record it and screen share. There we go. Okay. Make that small. All right, so this is the SI session. So we're going to start by going over the notes from Wednesday and then just going into a bit more detail, understanding them a little bit better. And then we have a practice problem for a weak acid and a weak base that we'll do. So we'll start with the notes. Before she started getting into weak acid, she covered percent ionization. It's a smaller part of this unit, but it is a very important part. There'll be a few questions on your exam about this. And it's really simple formula that you need to remember. It's just the hydrogen hydrogen ion concentration divided by the initial concentration of the acid, HA. Once again, HA is just a general term for any acid. And so the example she gave us was if you have a 0.5 molar solution of an acid, so HA. What is the pH? H is 3.25. We're trying to find the percent ionization. So what we need to do is the molarity of the solution, the 0.5 molar, is going to be your concentration of HA. So you already have that solved. So percent equals, copy paste this, it's easier. Control C. There we go. Divided by 0.5 molar, 0.50 molar. Right, and then we need to find the hydrogen ion concentration. And so the way we do that is we look at the pH. So you remember last week we were going from the hydrogen ion concentration to the pH. And the way we did that was we took the negative log of the concentration. So pH is equal to the negative log of your H, your hydrogen ion concentration. But the way to solve for the hydrogen ion concentration is the inverse of that equation, which would be 10 to the negative pH. So you plug in your pH to that, you get equals 10 to the negative 3.25, which is equal to 5.6 times 10 to the negative fourth. So then this value right here is equal to your hydrogen ion concentration. So you plug it into the formula. So your formula would then read, can I paste this? 5.6 times 10 to the negative fourth divided by your molarity, which is 0.50 molar. And then since you're trying to find the percent ionization after you do all of that, so let's put it in parentheses. After you do all of that, you multiply it by 100%. And when you do this inside the parentheses, you get 0.11%, and then you get 0.11. Scratch that. You get 0.0011 which then multiplied by 100% is equal to 0.11%. So it's just important to remember this formula. But the really important part is to remember how to get the pH and the hydrogen ion concentration from one another. So these equations right here are the inverse of one another. This one we went over last week, and this is the one she covered on Wednesday. So that was it for the percent ionization. And then we got into the really important part of yesterday's lecture, which is weak acids and weak bases. You're going to be using this for the majority of the semester, so it's definitely important to remember how to do these. The main tip that I can give you is to memorize the strong acids and the weak bases, or the strong acids and the strong bases, because she'll give you a problem and it'll be, you have a 0.5 molar of hydrogen chloride. And you need to know that hydrogen chloride is a strong acid. But the opposite of that is she might give you a problem, 0.5 molar solution of HClO. If you don't know that that's not a strong acid, HClO is not a strong acid, then you might end up doing the wrong problem. So the best tip I can give you is to memorize the strong acids and strong bases. Does anyone know what some of these strong acids are? Why can I not pull up the chat? Oh, there we go. Okay. Anyone? There we go. Why is it doing that? Weird. Okay. Okay, so the strong acids, the ones that you'll need to remember, there's 7 of them, I believe. Pull them up real quick. It is hydrochloric acid, which is HCl. Nitric acid, which is HNO3. HNO3. Hydrobromic acid, which is just HBr. Sulfuric acid, H2SO4. Perchloric acid, HClO4. Hydroiodic acid, which is just HI, hydrogen and iodine, and chloric acid, HClO3. HCl. What did I just do? There we go. 1, 2, 3, 4, 5, 6, 7. Those are your 7 strong acids. So anytime you see these in a problem, you will know that you're working with a strong acid. And if you remember, strong acids dissociate completely, which is completely different than what we're going to be doing for weak acids and weak bases. So on the other hand, you need to know your strong bases. All right, here we go. NaOH, sodium hydroxide. KOH, potassium hydroxide. LiOH, lithium hydroxide. Rubidium hydroxide. Rubidium hydroxide. Cesium hydroxide. calcium hydroxide, H2. CaOH2 is calcium hydroxide. Barium hydroxide. We don't have the periodic tables in here. SrOH. That's strontium hydroxide. And then barium hydroxide. I think the formula is BaOH2. Yeah. It's BaOH2. All right, so those are your 8 strong bases. These are what you need to remember, because if you see these in a problem, it'll be a strong acid problem, but if it's something other than these, then it's going to be a weak acid and weak base, which is what we're about to get into. So we already all went over the ones that she gave us, so I'll get straight into our practice problems that I prepared. So we're going to start out with a weak acid practice problem. So we're going to start with, we're looking for what is the pH of a 2.00 molar solution of HNO2. Yeah. And then parentheses, the Ka, the equilibrium constant for an acid, is 4.5 times 10 to the -4th. And that is all the information she's going to give you for a problem. She's going to give you the pH, or she's going to ask for the pH, give you the molarity, and give you the Ka and the chemical compound. So if we compare this to our list of strong acids, we look here, it's not here. We have nitric acid, but we don't have nitrous acid, which is what this is. So we know that it's weak acid, which means that we need to solve it the way that she taught us. So let's take it step by step and y'all follow along with me if you have some paper. But we'll take it step by step following what she did and see if we can solve this. So the first step that she told us always to do, step 1, is to write down the reaction. So since it is a weak acid, we start out with HNO2. And I don't have the double-sided arrows, so we're going to use a equal sign, but that's the, right here. Oh. There we go. That'll work. That's just saying it goes both ways. And it's dissolving into a hydrogen ion plus the nitrate. Yeah, nitrate on NO2. And then, so that's step 1, is to write down your reaction. Then step 2, going down a little bit. It's not looking as good as I wanted it to, but is to write down the equilibrium reaction, which is where you plug in your Ka. So Ka is equal to, put it in parentheses so you all understand, H plus the concentration, because it's products over reactants. So you have your H plus ion times your concentration of the nitrous, which is there in. There we go. And those are your products. And then you divide that by your reactants, which is the HNO2. Okay, so now you have your reaction equation and you have your equilibrium equation. So what's the next step? The next step is to kind of dissect the problem. Get rid of these. So we know right here, this is time is equal to 0. This is before the reaction begins. So we know that the concentration of the nitrous acid is 2.00 molar. We know that from our problem. Then we go over to the hydrogen ion, and since it's before the reaction starts, it's at 0. And then we go to the nitrate, and it's also at 0 because the reaction hasn't started. You have no products yet. But then we go down here, and let's say this is time is equal to equilibrium. So this is while the reaction is at equilibrium. We don't know how much it's going to change yet. That's what we're trying to solve to find out. But we do know it's going to change by a certain amount. So let's say we have 2.00 molar from the beginning, and we're subtracting X from that. That's the amount that it's changing during the reaction. And if your reactant is changing by that much, that means your two products are both going to be that value. So all three of these values are the same. And then we're solving for what this is so that we can solve for the pH. So then we get into the math, the fun part. So we know that the Ka from the problem is equal to 4.5 times 10 to the negative fourth. Ka is equal to 4.5 times 10 to the negative fourth. And then we know from this equation right here that we need to plug in these values. So H plus is X, NO2 is X, and then HNO2 is 2.0 molar minus X. So we just plug that into this equation right here. We have the numerator, X squared, because you have two X's in the numerator, divided by the denominator, which is 2.00 molar minus X. And then if you remember, we have to see if we can drop this X right here. This X right here. Because if not, if we can't drop it, then we have to go and do the entire quadratic equation. And it takes a lot of time to do that. And if you're on an exam, you're going to want to do this as quick as possible. So the way we do that, if anyone remembers, if you remember, text it in the chat real quick. Never mind, because the chat will not pull up. Okay, never mind. 2.00 molar. So the way we find out if we can drop that X, we take the concentration, the molarity, and we divide it by the Ka. So divide it by 4.5 times 10 to the negative fourth. And what do we get whenever we do that? 2 divided by 4.5 times 10. Shoot. I need to bring my calculator next time. Divided by 4.5. Do you have a calculator? Oh, sweet. Can you do that real quick? 2 divided by 4.5 times 10 to the negative fourth. It doesn't work on my phone. No, I can't look it up on Google. How's the chats here? 2 divided by 4. You got it? All right, sweet. Okay. If you could do that real quick. Oh, you said you didn't have it?
No, I don't.
Oh, I thought, okay. Okay, so this is going to be equal to yeah. I'm gonna make all this a little bit bigger. $4,444. Basically, as long as this number is bigger than 1,000, you can drop that x, which it is. 4,444 is bigger than 1,000. So this x is pretty much going to be meaningless in the problem because it's such a small number. So we drop that x, or I'll keep it in for this part. And then we'll go down. And yeah, we'll drop that x. And that makes the problem much easier because then all we need to do is multiply this 2.00 molar to the other side. And then we are left with 9 times 10 to the negative, ooh, that was bad, negative fourth. That's just 2 times 4.5. And you keep the times 10 to the negative fourth because it doesn't get over 10, is equal to x squared. Then you solve for x from that. So you need to take the square root times 10 caret negative 4. And then take this number and square it. 0.03. So x is equal to 0.03. This is going to be a bigger number than most of your x's that you would get, but it's still the same principle. Most of your x's will still be something times 10 to the negative. But now we have x. And what does that mean for us? Well, if we go back up here, we know that x is equal to the hydrogen ion concentration. Move it over. There we go. X is equal to the hydrogen ion concentration. So we'll plug that in. The hydrogen ion concentration is equal to 0.03. But what do we do with that? Well, we're trying to find the pH. And if you remember, you come all the way back up here to the top. pH is equal to the negative log of the hydrogen concentration. So we have everything we need. We just plug this into our calculator, the negative log of 0.03. 0.03 log base 10 negative. And we come up with a pH of 1.522878, and it keeps going. So then we need to find our significant figures. So if we look at our hydrogen ion concentration, we have 2 significant figures. And because of the rules, that means that we go to the first 2 decimals of the pH. So the pH is equal to 1.52. And there you go. That's how you solve a weak acid problem. That seemed like a lot of steps. It's a lot faster whenever you're writing it on paper and not on a computer. It's a lot harder to control. But this is every step that you'll need to do. And then whenever you get to bases, it's a little different, but the same concept overall. So we'll go ahead and do my weak base problem, and that should be it for today. So we'll try and make this quick. So the weak base problem I have for us is we're trying to find the pH of a 0.100 molar solution of NH3 ammonia. And the Kb is equal to 1.8 times 10 to the -5th. Okay. And by the way, I don't think she ever explained this in the lecture, but so K is your equilibrium constant for the reaction, but then we have KB and we have Ka. I don't think she ever explained the difference. It's real simple. Whenever you're solving for acids, you'll get a Ka. A stands for acid. Whenever you solve for bases, you'll get Kb because B stands for bases. It's a really easy way to tell what type of problem you're working on, because let's say you get something that you don't know what it is. If you didn't know what NH3 was, you didn't know that was a base. You knew it wasn't a strong base or a weak base, but you didn't know if it was a base or an acid. Then you look at your Kb, you realize it's a Kb, and you're trying to solve for a base, which becomes really important later on, and we'll get to that part in just a second. All right, so let's look at her problem, and let's solve it going along the same steps she did. So remember, the first step is always to write the reaction. I'm not doing that again. Write the reaction. So the reaction is, she had the same chemical, so it'll be the same reaction. NH3. There. At that time. Cool. Oh, I forgot a part. It's plus H2O, which is a liquid, or it's viewed as a liquid, because it's the solvent. The ammonia is dissolving in the water, so it's considered the solvent in this equation, and that means it'll drop out in the Kb equation. And then that's becoming NH4 plus OH, NH4 plus OH. So that's step one. Then you come down here, and we are writing the Kb equation. So K B is equal to NH4 the concentration of the ammonium times the concentration of the hydroxide. Those are your products, so they're in the numerator. And then we drop out the water because it's a pure liquid, it's the solvent. And we leave the NH3, so the reactant is NH3, ammonia. All right, and then we go back and we do what we did earlier, where, come back up here, you start at T0 and you put in what your values are, then T equilibrium to see how much they changed. 10 minutes left, we gotta hurry. 10. Okay, so it's 0.100 molar. The water drops out. This is 0. And this is also 0 at the beginning of the reaction. Then we come down here to T equilibrium. T equals equilibrium. I still in subscript. Oops. This is 0.100 molar minus X. This is X, and this is X, because that's how much it's changing in the reaction, just like the way the acids worked. Then we know that Kb is equal to 1.8 times 10 to the -5th. And that is going to be equal to, when we plug in these values for these values, we get X squared divided by 0.100 minus X. And then we do the same thing that we did for the other problem. 0.100 divided by 1.8 times 10 to the -5th. And if that number is over 1,000, which it is, then we can drop this X. So Control C, I'll save you the time of doing all the math. We can drop the X in this equation. And then we solve it. So we multiply 1.8 times 10 to the negative fifth by 0.100. 1.8 times 10 to the fifth negative times 0.1. And we get 1.8 times 10 to the negative 1, 2, 3, 4, 5, 6. Okay. And that is equal to x squared. So then we're solving for x. X is equal to the square root of that, which is, there it is, 0.00134116. We go sig figs, we have 2, so it needs to be, again, x equals 0.0013. All right, so now we have x, which is equal to the hydrogen, so this is where the problems differ. So up until now, everything has been the exact same, except for KB versus KA. But now is where it gets different, and this is where it'll trick you on an exam. So whenever you solve here, you're not solving for the hydrogen ion concentration, you're solving for the hydroxide ion concentration. If you go back up here, hydroxide is equal to X. So that's the concentration of the hydroxide. So since that's the case, we can't find the pH of the hydroxide. We find the pOH of the hydroxide concentration. So we take the negative log, I'll say pOH is equal to the negative log of 0.0013. Plug that into the calculator real quick. Stupid calculator. Okay, log negative. And then we get the pOH, which is equal to pOH is equal to 2.886056. Okay, so then we need to find out sig figs. We have the zeros aren't significant, so we only have 2 right here. So we go to 2 decimal points and we round up because of the 6. So it would be pOH is equal to 2.89. Then the way to solve for pH from pOH, because she asked for pH, but you had to get pOH from here. So pH is equal to 14 minus your pOH. So 14 minus your pOH. 14 minus pOH, or 2.89. Calculator real quick, 14 minus 2.89. And you get a pH is equal to 11.11. And that will be your final answer. And you check it by saying, you see that's a base, so you know it needs to have a pH higher than 7. And that's exactly what it is. It's 11.11, so that checks out. And you know that you're at least in the right half of the right answers. And also, if you ran that check on our pH of the acid, where'd it go? There it is. pH of 1.52, that is a pH less than 7, which is what you want for an acid. So that's about everything that I had for today. I think we're running right out of time. We have 4 minutes left, so if anyone has any quick questions, now would be the time. And also, I think I need Juan, can you send me your student ID number so that I can take attendance for you? Awesome, thank you. Okay, do either of y'all have any questions real quick? If not, that's the end of the meeting. Y'all have a good day. They all left.